We will start talking in this lecture about engine types, geometry, performance, and engine charging. First of all, there are different specifications for the internal combustion engine. Okay. First, we need to define what is an engine. Engine is a device that converts fluid energy to mechanical motion. Okay? We know what are the powers that exist in the car. Fuel power, which is a mechanical, which is chemical power, stored in the fuel. When the fuel enters the engine, and for if we are talking about gasoline engine, a spark is ignited, or if we'll be talking about diesel engine like this term, it will be with the self-ignition. Whenever the fuel is combusted, it turns the chemical energy into fluid energy. We have exhaust gases with high temperature and high pressure. These exhaust gases exert force on the piston, so we get a mechanical movement from the piston. So an engine is a device that converts fluid energy into mechanical motion. The power that is generated during combustion, is it fully utilized inside the engine? No. Part of the power is useful mechanical work that is used to drive to provide power from the engine, and the rest of it is lost to the surrounding in the form of heat. Okay? Depending on the ratios of both of these powers, the efficiency of the engine is determined. We have two main types of combustion engines, internal and external. Internal combustion engines are like the vehicle engines, like the gasoline and diesel engines. External combustion engines are like boilers and steam. The boilers that are used with the steam generation or the steam power plants. So what are the main differences between internal and external combustion engine? It depends on where the power is generated and where the power is extracted, okay, and which fluid produces the power and which fluid extracts the power. For the internal combustion engine, where does the combustion occur? Inside the cylinder, over the piston. Where do we extract the power? From the piston inside the cylinder. So the combustion and the power generation are in the same place. Okay? What fluid generated the power? The exhaust gases that are combusted. What fluid generates the fluid that has the high power is the exhaust, the combustion gases, and it exerts the pressure and the force on the piston to generate the power. So the same fluid that has the energy is the one that exerts the power that is generated as mechanical work from the engine, and the power is generated and extracted in the same place. So this is an internal combustion engine. But what about the boiler for a steam power plant? What is the main fluid that exerts the power in a steam power plant? Steam. Okay? How do we generate the steam? We have a boiler that we use fuel, gasoline, diesel, whatever the fuel it is. We burn the fuel. A heat exchanger takes the energy from the fuel and heats water to convert it into steam. Then this steam goes and turns the turbines of the steam turbine to generate the power. So is the combustion place and the power generation place are the same? No, the combustion is inside the boiler. The power extraction is in the steam turbine. Does the same fluid do both processes? No. The fluid that generates the heat is the fuel and the exhaust. The fluid that exerts power and generates mechanical power is the steam. So, not the same place and not the same fluid. So, this is an external combustion engine. Okay? We have different classifications for the internal combustion engines according to the application, whether they are passenger cars, trucks, locomotives, aircrafts, or marine applications. According to the engine design, there are inline engines, V-type, W-type, or horizontally opposed and radial engines. Do you know the difference between all of them? Or not?
Arrangement of cylinders.
Okay, the arrangement of cylinders. The inline engines, let's go over them quickly. Inline cylinders, all the engines are on the same line. Amen? Okay? But what if we want to increase the power? If we want to increase the power, we increase the number of cylinders. So if we, instead of 4 cylinders, we make it 6. The length of the engine will be 50% more. What if we want it to be 8 cylinders? The length is now doubled from the 4-cylinder engine. What if we want to make it 12 cylinders? The length will be tripled. Okay? So where do we put this long engine? You know, in vintage cars like the Cadillac and in vintage cars like Cadillac and Pontiac, the old American cars, you can see that the maybe the engine bay, okay, in the front of the car is very long, okay, to house a very long engine, okay. But having an engine that is very long, it takes the space from the inside cabinet of the car, okay. So how to make the engine produces the same power and make it even shorter? If we put the cylinders beside each other. So they invented the V-type. We have two pistons moving with an angle of approximately 60 degrees, making a V shape. Okay? So if we have a V8, it will be the same length as an inline 4, but it will be slightly wider. Okay? So what if we want to increase the power more in a confined space? They designed the W-type. In the W-type, we have 3 pistons in the same plan, 2 in the shape of a V and 1 in the middle. Okay? So a W12 will be the same length as an inline 4, but it will be triple as wide. Okay, but as the width of the inline cylinders is small, so a triple the width isn't that large. Okay, so now you can increase the number of pistons and increase the power obtained in a confined or in a smaller space that can fit under the hood. What about the radial engine? Radial engine is mainly used in older type airplanes. Okay, you want just a fan, a rotor that is installed in the center to rotate, to generate the thrust. So we arrange the pistons and cylinders around its axis. Okay, there is also the opposed cylinder engine or the horizontal engine. The opposed cylinder or the horizontal engine, instead of the pistons moving up and down, they move left and right. So what happens to the height? The height is minimized. It's very small. Okay? But what about the width? Or the area of the engine? It becomes larger. Okay? So what is the purpose of why do you use such a horizontal engine? We can use it in a sports car. Okay? We need the center of gravity of the vehicle to be as low as possible and in the center of the vehicle to make it stable. So what is the heaviest part in the vehicle? The engine. So what if we put the engine in the middle of the car and as low as possible? It will make the car stable. But if we put an inline or a V engine or a W engine inside at the center of the vehicle, the seats will be very high and the vehicle won't be stable. So if we convert the engine into a horizontal engine, it will have a very low height, so it can be put under the vehicle, under the seats of the drivers. Okay? And the horizontal engine is usually used in race cars or high performance cars. The engine classification, another classification is according to the working cycle. You could have a 4-stroke cycle or a 2-stroke cycle. According to the fuel type, it could be gasoline or diesel or natural gas. Another classification is according to the method of fuel mixing. Okay? What is the method of fuel mixing? We have two main methods: homogeneous mixing and heterogeneous mixing. Which one is used for the gasoline engine? Homogeneous mixing is used for the gasoline engine, and heterogeneous is used for diesel engine. Homogeneous means that both air and fuel mix very well before combustion, which is the case in gasoline engine. In gasoline engine, the fuel starts mixing with the air at the intake, before the intake valve, in the intake manifold. And it mixes during the intake stroke and during the compression stroke. So the mixing is very well, and it's called the homogeneous mixture. But in diesel, we inject the fuel at the end of the compression stroke. So it has very, very short time to mix with air. So it's called the heterogeneous mixing, and the mixture of air and fuel isn't that good. Another classification is according to the method of ignition. In gasoline engine, we use sparks from spark plugs. But in diesel or in compression ignition engine, we do not use spark plugs. We rely on the self-ignition of the fuel. We compress the air at a very high compression ratio to heat it above the self-ignition temperature of the fuel. So when the fuel is introduced inside the cylinder, it ignites right away. Okay? Another classification is according to the method of load control. Okay? How do we control the load in gasoline engine? We press the accelerator pedal. What happens when we press the accelerator pedal?
It's open the throttle.
The throttle is opened. What happens when we open the throttle? What?
Inside here.
Exactly. When you open the throttle valve, the amount of air increases. As the amount of air increases, the airflow sensor senses this increase and accordingly increase the fuel injected at the intake valve. So you increase the air, and as the air increases, the fuel is increased accordingly. But what about in diesel or compression ignition engine? Compression ignition engines are unthrottled. Okay? They do not have throttle valves. So all the time, the passage of air is fully open. So what if I want to increase the power or increase the load? We only increase the amount of injected fuel. But at a specific RPM, the amount of air is always constant regardless of the load. Okay? So, in gasoline engines, we control the air with the accelerator pedal. In diesel engines, we control the fuel with the accelerator pedal. Okay? Finally, the method of cooling, we can have a water or air cooled engine. The engine operating cycles, we have the 4-stroke cycle, intake, compression, صدق من هنا تصدق أنا أول مرة أسمع إن في صوت. تمام. No. بقالي 4 سنين بدرس المادة في حدود 10 مرات اتدرست لحد دلوقتي أول مرة أعرف إن الفيديو ده فيه صوت. These are the main components of the engine, just a review so that you can remember the main parts. The piston moves between the top dead center and the bottom dead center. The volume between the top dead center and the bottom dead center is called the displacement volume. Okay? And the volume that is between the top dead center and the cylinder head is the clearance volume. Okay? This is a PV diagram of the 4-stroke engine. These numbers, approximately every time, maybe 60 or 70% of the students mix these numbers up. Okay? How many crank revolutions per cycle of the 4-stroke engine? How many crank revolutions per the cycle of the 4-stroke cycle? Two. The 4 strokes, the intake, the piston moves downward and the crankshaft rotates half rotation. So single stroke is a half crankshaft revolution, and it's a 4 stroke, so a single stroke is 25% of the cycle. Okay? The camshaft rotates at half the speed of the crank shaft. So 1 stroke represents quarter revolution of the camshaft. Okay? في الآخر السايكل الواحدة لفتين كرانك. Okay? الستروك الواحدة نص لفة كرانك وربع لفة كام. Okay? ده بالنسبة للفور ستروك سايكل. Now we need to check the 2-stroke cycle. 2-stroke cycle means that the full cycle happens in how many crank revolutions? 1. 2 strokes. Each stroke is a half crank revolution. So 2 stroke in 1 crank revolution. Okay? Let's see how this happens. The valves are replaced with ports. This one is the intake port, and the other one is the exhaust port. Let's check it again. When the piston is moving downwards, okay, as the piston goes down, the air comes in through the crankcase, the air and fuel, and mix inside the crankcase. As the piston goes down, it compresses the air in this area. So as the piston opens the intake port, the compressed air inside the crankcase rushes inside the cylinder. And as it rushes inside the cylinder, it displaces the exhaust and pushes it out through the exhaust port. Okay? So, in the same stroke, you do intake and exhaust at the same time. Let's continue. Now, the piston moves up. As it covers both the exhaust and the intake, it starts the compression. At the top dead center, spark is ignited and the power is generated, and the process repeats itself. If you check it, you will see that the exhaust port opens slightly before the intake port to allow for the highly pressurized exhaust gases to exit first. If I open the intake port first, the exhaust gases pressure is higher than the intake. So some of the exhaust will push and go inside the crankcase, and we don't want that. We want the high pressured exhaust to exit first. Okay? But how about the quality of the charge? The quality of the charge is very low. Why? Because you do not wait for all the exhaust to exit. During the exhaust exiting, you input the fresh charge. And does fresh charge displace all the exhaust to the outside? No. Part of the fresh charge mixes with the exhaust, and part of the exhaust remains inside the cylinder. And part of the fresh charge exits from the exhaust port. So the overall cycle efficiency is what? Is lower. But which engine is better? Is it 2-stroke or 4-stroke in terms of power? No, 2-stroke. Why? You get power stroke, 1 power stroke per cycle. Okay? So in the 4-stroke cycle, the crankshaft rotates 2 revolutions and you get 1 power stroke. But in the 2-stroke engine, the crankshaft rotates 1 revolution and you get 1 power stroke. So, on paper, the power of the 2-stroke engine is double the power of the 4-stroke engine. So, do you see 2-stroke engine used in cars? No. Why? Because the quality of the combustion is low. Okay? And also, the fuel and air enter through the crankcase, and from the crankcase it enters the cylinder through the intake port. So what is there inside the crankcase? The oil. So during the intake air entering the crankcase, it might mix with some oil vapors and suck them inside the cylinder. So in all 2-stroke engines, you refuel it with fuel and oil, because oil is burned inside the cylinder. Because there are no gaskets that separate the oil from the cylinders. Okay? We have the 2 strokes are called the exhaust blowdown and the scavenging. Okay? During the piston going up, the scavenging is when the air enters the cylinder and the exhaust and intake ports are closed, and we start the compression. The exhaust blow down is when the piston moves down and the exhaust exits and the new fresh charge comes inside the cylinders. You can see that there are no dedicated stroke for either the intake or compression or power or compression. Okay? You see that at the same time, in the same part of the stroke, two processes could happen at the same time. Of course, in two-stroke engine, every stroke represents half cycle and half crankshaft revolution. So the cycle, the two-stroke cycle, happens in one crankshaft revolution, while the four-stroke cycles happens in two crankshaft revolutions. Now we will start talking about engine geometry. Did you study these equations before? The VD and the compression ratio? No, I mean the VD and how to calculate the compression ratio and the displacement volume. Okay, we'll go through them quickly. Okay. As I mentioned to your colleagues before you came here, I will try to decrease the amount that I dedicate to equations or to problem solving, because of the tight time. We have already lost 3 lectures, and the time in Ramadan will be very short. So the second of thermodynamics and the dissociation will be only explained in tutorials. Okay?
But they're coming in the terms and Bible. They're coming in this.
معانا. All topics are included in the terms and findings. Okay? If something is cancelled, I will clearly say it's cancelled. Okay? Second law of thermodynamics and dissociation will be explained in tutorials. Okay, and you will get tested in the midterms on them. Okay, we're just trying to clear some time. Okay, we're going to, this term we will explain diesel engines, which will consume a lot of time. Okay, so I will try to use this time in lectures to explain diesel engines and emissions. Okay, and the problems I know is that you mainly rely on the tutorials for problem solving. Okay, so for the engine geometry, you see the first equations first for the terminology, the S, which is the distance, the vertical distance between the center of the piston and the center of the crankshaft. A is the crankshaft radius, L is the stroke, B is the bore diameter. Okay? So I believe that the equation that you already know is the VD, which is displacement volume. This volume is the area of the volume of the cylinder, which is pi over 4 B square times L, and times N, which is the number of cylinders. Pi over 4 B square L is the volume of one cylinder. According to the number of cylinders, we multiply it by N. Okay? And the compression ratio, RC, is the maximum volume over the minimum volume. Maximum volume, which is what? When the piston is where? At the bottom dead center. So the volume above it is the VD plus the VC. Okay? over divided by the minimum volume. The minimum volume is when the piston is at the top dead center. So the volume is VC. The compression ratio is VC plus VD over VC. Okay? And be careful, because many times I see it, you calculate the compression ratio as VD over VC. The numbers will be very close because VC is small. Okay? But it will be wrong. What about those equations, the S of theta and the V of theta? You are not required to memorize these equations. They are just for your knowledge, especially if you are doing some maybe research work or some simulations. Okay? Because as the piston moves, this distance changes as well as the volume above the piston. The volume above the piston changes from VD plus VC to VC. Okay? And how do we know the exact volume above the piston or inside the cylinder? According to the angle of theta of the crank shaft. Okay? So from this equation, from V theta, we calculate the volume above the piston inside the cylinder at any crank angle degree. Okay? You will only need to use it if you are going to do some research or simulation work. Okay? Other than that, you are not required to memorize it. And also, as a rule of thumb, normally the stroke and the bore are equal in many engines and they are called the square engines. Okay? So if I give you an engine and I give you only the bore, I didn't say anything about the stroke, and there is no way for you to deduce the value of the stroke, you will assume that the engine is what? Square engine and B equals L. Okay? But first, before you assume that, you need to check that I didn't give you any other information that you can figure out the stroke from it. Okay? When we calculated VD is the displacement volume. Okay? This displacement volume is filled with fresh charge, which is mainly air plus fuel, but you know that the air to fuel ratio is large. It's approximately 14.5 or 14.7 for stoichiometric combustion. Okay, so the mass of air is 14.5 times the mass of the fuel. So as an approximation, we assume that all the intake is air. So the mass of the intake air is Vd times rho, the density of the air. Correct? But if I said that the intake mass is Vd times rho, is it actually the actual mass that enters the cylinder? No. Why is that? Because the intake time is very, very short. Okay, let's give it an example. Let's assume that the engine is rotating at 3000 RPMs. 3000 RPMs means that the engine rotates 50 revolutions per second. Okay? So the time of the revolution is 20 milliseconds only. So the time of the intake stroke is what? 10 milliseconds, half crankshaft revolution. So, do you think that 10 milliseconds will be enough for the engine to draw the total mass of air inside the cylinder? It won't be enough. Okay? So, here comes the term volumetric efficiency. Okay? Which this efficiency calculates the effectiveness of the engine intake. How do you calculate it? You calculate it as the actual mass that went inside the engine over the theoretical mass that should go inside the engine. The theoretical mass is Vd times the density of the air. Okay? And the actual mass is measured. If the actual mass is the same as the theoretical mass, so we have perfect intake. And the volumetric efficiency is 100%. Okay? But usually the amount is lower, the volumetric efficiency is lower than 100% due to the very short intake time. Okay? We also, as an engine geometry, we would like to calculate SP, which is the average piston linear speed. Okay? Is the piston speed constant? No. At the bottom dead center and the top dead center, the piston linear speed is what? Let's take it, the piston is going up. The velocity of the piston, the linear speed of the piston is high. As it approaches the top dead center, it gets slower. As it reaches the top dead center, the linear speed reaches what? 0. And then the piston reverses its direction. So the velocity starts to increase till it reaches a maximum at approximately the mid space between top and bottom dead centers. And when it reaches the bottom dead center, it reduces again and returns to 0 and inverts its direction again while it's going up. So we need to calculate an average speed of the piston across the cycle. The rule for engine piston, average piston speed average linear piston speed is 2Ln. L is a stroke, 2 is 2 times the stroke, and the N is the RPS, because we calculate the speed in meters per second. Most mistakes happen when you use N in RPMs. You calculate the speed as meters per minute, not per second. Okay? What about engine power? We have 3 main powers: indicated, brake, and friction. Okay? As I said at the beginning of the lecture, I said the main power comes from the fuel, which is chemical energy. Chemical energy is converted into fluid energy after combustion through the thermal efficiency. Okay? The fluid power, which is pressure and temperature, are the indicated power that pushes the piston downwards. Okay? Does all the indicated power that pushes the piston downwards is utilized as output from the engine? No, because there is friction. Friction between the piston and the riders, friction between the valves, friction in the crankshaft, friction in the camshaft. All these frictions make you lose some power. So the brake power, which is the power delivered to the crankshaft, must be lower than the indicated power. And the difference between them is the friction power or the friction losses. Okay? And the ratio of the brake power over the indicated power, it is the mechanical efficiency of the engine. So you need to differentiate between the thermal efficiency and the mechanical efficiency of the engine. The thermal efficiency is mechanical power over thermal power. Okay? Mechanical efficiency is mechanical power over mechanical power. Okay? Of course, you know that when you try to calculate torque is related to power, as power equals torque times omega. And omega is 2 pi n. And of course, as in all calculations, as I mentioned, n is in what units? RPM per second. Okay, not minutes. Because we use SI. SI units, they do not consider minutes. They consider only seconds. How do we calculate the indicated power? Okay, power is work per unit time. Okay, so how do we calculate the indicated work from the engine? The indicated work that occurs inside the engine is calculated from the area under curve of the PV diagram of the engine. Okay, if you calculate the area under the curve, or in another term, you integrate the PV diagram, you get the indicated work. Okay, you divide the work by time units, you get the power. Okay, so if we try to calculate the power, it's work per cycle, which is this. If you integrate this curve, you get the work per one cycle, right? So it's work is kilojoule per cycle. Okay, you need to multiply it by cycle per second to get kilojoule per second, and to get power, which is watts or kilowatts. Right? So how do you get the cycle per second? The number of cycles per second depends on two things: the RPM and the configuration of the engine. Is it 2 strokes or 4 strokes? Because if the engine is 4 strokes, how many cycles? And it rotates at 3000 RPM. How many complete cycles does the engine do per second? No, I'm asking if the engine is rotating at 3000 RPMs. Okay? How many cycles does the engine do per second? What is RPM? Or let's make it, sorry, how many cycles does the engine do per minute? Not second. The engine is rotating at 3000 RPM. How many cycles does the engine do per minute? RPM is revolutions per minute. Okay? So if the engine is 4-stroke, the full cycle takes 2 revolutions. So if the engine is rotating at 3000 RPM, then the engine is performing 1,500 cycles per minute. Okay, so you divide the number of revolutions per n, which is 2 for the 4-stroke cycle. Okay, but what if the engine is 2-stroke cycle? It performs complete stroke per 1 revolution. So, if the engine is sitting at 3000 RPMs, it will be doing 3000 cycles per minute. So, N is equals 1 in this case. So, N is 2 for 4-stroke engine and 1 for 2-stroke engine. Okay? I mentioned that the mechanical efficiency is the ratio between the brake power, which is the output mechanical power, over the input mechanical power, which is the indicated power. Okay? And the difference between the indicated and the brake power is the friction power. How do we increase engine power? How can we increase the power from an engine? You can increase its speed. Okay. You can increase its displacement. And you can increase the compression ratio. Okay? But is it all straightforward and all the way proportional? No. Let's check the relation between power and torque versus the engine speed. Okay? You see that, let's check the torque curve at the bottom. As the RPM increases, the torque increases until it reaches a point and then it starts to decrease again. Okay? Why is that? And the same for power. You can see that the same power curve for different displacement, as the displacement volume increases, the power and torque increase. But as the RPM increases, not always the power and torque increase. Why? Because for the power, at higher speeds, okay, how many powers did we mention that exist inside the cylinder? Indicated, brake, and friction. Okay? As the RPM increases, okay, as the RPM increases, the fresh charge rate increases. So the number of cycles increases. So you burn more fuel. So the indicated power increase. Okay? But as, again, the engine speed increases, the piston speed also increases. What is the relation between friction and speed?
At higher friction, the speed is low. Friction is high.
At higher what?
Higher friction, the speed is low. Under the friction is high, the speed is low.
No. The speed is the one that generates the friction, not the other way around. So if the speed is high, the friction is low or high?
Friction is low.
Friction is low. So if you are cold and you want to heat you, warm your hands, you move it slowly like this or quickly? Quickly. So as the speed increases, the friction increases. Okay? And more heat is generated. This generated heat, is it useful heat that I can use it, or is it lost as heat losses? It's lost. So as the speed increases, the friction increases. So as the speed increases, indicated power increases and the friction increases. So the brake power starts to decrease at higher speed because the friction power increases. So why? So this is the reason why the power, the brake power gets or reduced at higher RPMs. So why the power is still low at lower RPMs as well? What?
Heat losses.
That's correct. That's due to the heat losses. If the engine is running slowly, okay, So there is more time for the combustion heat to transfer through the cylinder walls to the coolant instead of pushing the piston downward. So at low speeds, the heat losses is very high, so the brake power is low. At higher speeds, the friction power is so high, so the brake power is also low. As there is only one optimum point, which is the maximum power point or maximum torque point, here for the torque and here for the power. Before and after this point, we get a loss in power and torque. And by the way, the maximum brake torque and the maximum brake power points shouldn't be at the same RPM. They can be at different RPMs.
Why so?
Eh?
Why so? Why?
Why? Because the power, you can see that the power is the maximum brake power at higher RPM than the maximum brake torque. Okay? Because it depends on the speed of the engine. You know the relation between power? Power as a power, it is a matter of heat supplied to the engine to move it. Okay? But torque is power over omega. Okay? So, when the power increases and the RPM is still low, so the torque is what? It's high. So the torque is higher at lower RPMs. But when you reach the point of maximum power, the maximum power occurs at very high RPM. So you divide the maximum power by larger RPM. So you get a lower brake torque. Okay? The RPM plays a role in here. We have another term that's called mean effective pressure. If you remember, previously we mentioned the mean piston speed, which is what the average linear speed of the piston across the whole cycle. Okay? Because the speed is varying across the cycle. So, what is the mean effective pressure? Is the pressure constant throughout the cycle? No, we saw the PV diagram. It's not constant. And if you want to calculate the work, I said that the work is the area under the PV curve. Can you easily calculate the area under the PV curve from the PV diagram that we saw? No, you need to perform complicated integrations. But what if we said that there is a term called mean effective pressure, which is the average constant pressure across the whole cycle? Okay? So if you want to calculate the work, the mean effective pressure is a constant value, so it will be a rectangle that you calculate the work from. It will be the mean effective pressure times the VD, the displacement volume. Okay? Which you get, the work is the mean effective pressure times the VD. Okay? And you know we can calculate work to power by dividing by time. And the same thing we can do to VD, we can convert it to V dot D. We divide the VD by time, okay? So we can, mean effective pressure is power over V dot D. When I say a term like power or work in general, it can be indicated power, which if we put the indicated power here, we will calculate the indicated mean effective pressure. If we use the brake power here, it will be the brake mean effective pressure. And if we use the friction power here, it will be the friction mean effective pressure. Didn't we say that indicated power equals friction power plus brake power? Okay? If we divide all these powers by V dot D, you will get that indicated mean effective pressure equals brake mean effective pressure plus friction mean effective pressure. Okay? Which is written here. All these points we discussed earlier. Now there is another term that's called specific fuel consumption. Okay? What is a specific fuel consumption? It is the amount of fuel consumed to produce one power unit. Why can't we depend just on saying that the fuel flow rate is an indication for the fuel consumption? Why? If a car consumes, for example, let's say 10 liters per 100 kilometers, and another car consumes 11 liters per 100 kilometers, which one is more efficient? The one that consumes 10 liters per 100 kilometers. No, there is missing information. What was the load of both vehicles? Maybe the one that consumed 10 liters per hour was an empty vehicle, only the driver inside it. Okay? And the one that is consuming 11 liters per 100 kilometers, all 5 passengers are inside, and it has load in the trunk as well. Okay? So when you are calculating the fuel efficiency, power is a major player in calculating the fuel efficiency of an engine. So, instead of using general fuel consumption, you need to know how many kilograms or liters of fuel are consumed per unit power. Okay? So, the fuel consumption, specific fuel consumption is m dot fuel per the power. Okay? We also have brake power and indicated power. So it can be brake specific fuel consumption, and it can be indicated specific fuel consumption. Okay? What is the relation between the specific fuel consumption and the engine size? You can see from the first graph on the left that as the displacement volume increases, the specific fuel consumption decreases. Why is that? Because as the volume of the engine increases, the surface area decreases. So the heat transfer through the surface area is lower at larger V displacement volumes. That's why the specific fuel consumption is lower at larger displacement volumes. Okay? And of course, cylinder bore is a direct function of displacement volume, so of course, specific fuel consumption gets lower as long as you increase the cylinder bore. Okay? What about the specific fuel consumption versus the speed? Specific fuel consumption, this is the brake specific fuel consumption. Do you remember the power curve that we drew earlier? The power was lower at low RPMs. then increased, then got lower again. Okay? The specific consumption is m dot fuel over the brake power. So the brake power is inverted. So you can see that this curve is the inversion of the brake power curve because you divide by the brake power. So at lower RPMs, the brake power is low. So when you divide by a small number, the value is what? Is higher. So you get a higher brake specific fuel consumption at lower RPMs. When the power increases, it gets lower. Then the power decreases again. So the fuel consumption gets higher. Of course, there's another factor that controls the brake specific fuel consumption, which is the compression ratio. If you increase the compression ratio, we mentioned earlier, how do I get a better efficiency and better power? I said you can increase the compression ratio. So as you increase the compression ratio, the specific fuel consumption decreases, which is an indication of a better efficiency. Okay? These are the both curves for the brake power and the brake specific fuel consumption. You can see that both curves are inversion from one another. Okay, specific fuel consumption is higher at lower powers and gets lower at higher power and then gets higher again at lower powers. And as the compression ratio increases, the power increases and the specific fuel consumption decreases. What about the brake specific fuel consumption versus the mean effective pressure? Okay. As the mean effective pressure increases, what is the rule of mean effective pressure? Is power over V dot D. Okay? So, if the mean effective pressure is higher, it means that the power is what? Is higher. So as mean effective pressure increases, the power increases. So as the power increases, the specific fuel consumption what? Decreases as well. Okay? And of course, as the RPM increases, how does this generally affect the fuel consumption? If you increase the RPM, you increase the number of cycles. So as you increase the number of cycles, you increase the fuel consumption. So as the RPM increases from 2000 to 4000, the fuel consumption increases. But the curve for the specific fuel consumption is still the same. Okay? The last curve is the air-fuel ratio versus the brake specific fuel consumption. You can see that, we mentioned earlier that the best combustion occurs at stoichiometric conditions. Okay? When you go with lean combustion, the amount of air is very high. So this extra air cools down the combustion gases. So it can reduce the efficiency. And if you get the fuel, make the mixture rich. So there is not enough air to combust all the fuel. So you do not get very high power. Okay? So you get the highest power at the stoichiometric condition. And the highest power corresponds to what? Lowest brake specific fuel consumption. They are all the curves that I'm explaining here are all related that you understand the relation between efficiency and power and fuel consumption. And the relation with the RPM and the compression ratio. If you understand these basic relations, you will get all curves correct. Because I might ask you to draw the relation between maybe the air-fuel ratio and the brake specific consumption. I could ask you to draw this curve. Not with dimensions, no, but just an indication. Okay? As for the combustion efficiency, combustion efficiency measures how did the fuel chemical energy transform into heat within the combustion. Okay? So any efficiency is an output over an input. The output from a thermal efficiency, the combustion efficiency, is the heat input that is gained inside the cylinder. So it's Qin, which is the heat added by the combustion cycle inside the cylinder, divided by the input. What was the input to give me this heat? It was the fuel. So over the M fuel times its heating value. Okay? What about the thermal efficiency? We have mentioned how many efficiency? 3. Combustion, thermal, and mechanical. I mentioned these 3 efficiencies. Combustion efficiency is what? It's an output combustion. The output is a combustion heat, which is the heat added to the cylinder, over the input, which is fuel. Okay? What is the thermal efficiency? The thermal efficiency is the conversion of thermal power to mechanical power. So the output of the thermal efficiency is mechanical power or work over the heat input to the cylinder, which is what? The combustion efficiency times the fuel flow rate times the heating value of the fuel. Okay? What about the mechanical efficiency is mentioned earlier. Mechanical efficiency, what does it mean? That both inputs and outputs are mechanical. Okay? So, mechanical efficiency, the output mechanical power is brake power, and the input mechanical power is indicated power. So, the mechanical efficiency is brake power over indicated power. So, I explained so many terminology till now. Okay? All of them you can easily deduce by understanding the meaning of each term. From all these terms, it can change from an indicator to friction to brake. Okay? So I don't want you to panic or memorize these things. No, you need to understand what is the meaning of mechanical efficiency, thermal efficiency, combustion efficiency. What is the difference between indicated, brake, and friction? If you know these meanings, you will get every term of them right. Okay? Look, neglect this arbitrary efficiency. It's not usually used, and it will just complicate things a little. Now the performance maps. From the previous figures, we are comparing between the speed and the fuel consumption and the power and the mean effective pressure, all of these. Okay? So, how do we control the fuel consumption and the fuel injection inside the engine? Controlling the fuel injection inside the engine and controlling the power depends on the engine speed, okay, and the throttle position. Okay, so you can see that all these lines, as you move up, you open the throttle valve wider. So as you open the throttle valve wider at the same engine speed, what happens to the power? Increases. What happens to the mean effective pressure? Increases at the same speed. Okay? So all these vertical curves are for wider opened throttle valve until you reach the top one, which is the wide opened throttle. Okay? So what happens to the power with RPM? It increases as you increase the RPM till you reach a limit, then it drops again, right? Check this line maybe. You see that it increases, then it drops again. This line also, it's neglect the first part, it's for another cases here. It increases and drops, increases and drops, increases and drops. Okay? You will see that each one of those lines has numbers beside it. What is this number? It's the specific fuel consumption at this line. Okay? So, as you go through these lines, you can see that the fuel consumption, spare fuel consumption is high. As you go up, it gets lower. And as you go up again, it gets higher. Why is that? At lower mean effective pressure. It means lower power. So at lower power and at the same RPM, when you calculate the specific fuel consumption, specific fuel consumption is what? M dot fuel divided by the power. So the power is small, so the specific fuel consumption is what? Is high. As you increase the power, what? The fuel consumption starts to decrease until you reach a limit. That again the power starts what? The efficiency drops and the fuel consumption starts to increase again. Okay? You see that the engine speed is the bottom x-axis and the top x-axis is the mean piston speed. Isn't the mean piston speed is 2 Lm? So it depends on the RPM. So if you know the stroke of the engine, you can calculate the mean piston speed. And from this graph, I can ask you to calculate the stroke. How you calculate the stroke? You will take any value, maybe this 6, it equals 2 Ln. You go down there and you find the corresponding speed. The only unknown is the L, which is the stroke. That's why I said at the beginning, you can assume square engine if I didn't give you any indication on how to calculate the stroke. Okay? So how do you use this map? I will give you a point. Maybe I will say that this engine is producing 600 kilopascal brake mean effective pressure, and the fuel consumption is 305 gram per kilowatt hour. So we'll just go here. Where is the line for the 305? This one. You will go just like this until you intersect with this point. Maybe at this point I will ask you, what is the mean piston speed?
Go down.
Just go up. Mean piston speed, you go up. What is the RPM? You go down. Okay? Maybe I ask you, what is the fuel consumption? How do you calculate the fuel consumption? Isn't the fuel consumption in kilograms per second? Isn't it related to the brake fuel consumption? And you know that, which is 305. You need to know the brake power. How can you know the brake power? From the mean effective pressure. So you get the brake power from the mean effective pressure and you put it here, then you get m dot fuel. Okay, so you see it's all connected together. These maps are 2D maps. They are a representation for the actual engine mapping, which are 3D maps. If you look at it from the top, okay, and you take 6 sections, you get these rings. Okay, this one is inside the ECU of the engine. It's a 3D map. So the engine knows the RPM, okay, and maybe the fuel flow, and knows the torque right away. Okay? What is engine charging? Okay? Engine charging means you remove the exhaust gases from the engine and replace it and refill it with new fresh charge. Okay? Which is the process of intake and exhaust. So, for a 4-stroke engine, you know that the exhaust stroke, there is a dedicated exhaust stroke and a dedicated intake stroke. Okay? And you know also that there is an overlap, very slight overlap, when the intake and the exhaust valves open at the same time. But it's for a very short time. So, what do you expect the quality of mixing of engine charging in the 4-stroke engine? No, it will be very good quality. Why? Because first you open the exhaust valve only. You make all the exhaust go away. Then you open the intake valve and you draw the fresh charge. So only you get the residual exhaust in the VC. That is the only exhaust gas that doesn't get out. But in the 2-stroke, you rely during the scavenging stroke that the intake air will push the exhaust outside. So you will get low quality. According to the engine type, if it is a 4-stroke or 2-stroke, you can have naturally aspirated engine or a turbocharged engine. Okay? Naturally aspirated means that the intake is drawn inside the engine with the suction of the piston as it goes down. If it is a turbocharged, you have a turbocharger that is driven by the exhaust to compress the air that enters the cylinder. Okay? Why do we use turbochargers? Because as you use turbocharger, you compress the input air, the intake air. As you compress the intake air, you increase its mass. As you increase its mass, you are working at a constant air-to-fuel ratio. So as you increase the air's mass, you increase the fuel's mass. So you get more power. That's why we use turbochargers. So how do we know the charging efficiency? Charging efficiency is the actual fresh charge that enters the cylinder over the theoretical mass that could enter the engine. Isn't it the volumetric efficiency we previously mentioned? Correct? This is correct for the 4-stroke cycle. Okay? And as we mentioned, the theoretical mass, it depends on rho times VD. VD times N over I over 60 is the V dot D. Okay, that we get from it the volumetric rate per second. In the four-stroke cycle, the charging efficiency is the volumetric efficiency that we previously mentioned. But in the two-stroke, okay, in the two-stroke, we have two factors, which is the delivery ratio and the scavenging efficiency. So before we continue, the charging efficiency for a four-stroke engine is what? The volumetric efficiency, which is the actual mass that entered the cylinder over the theoretical mass that could enter the cylinder. The maximum value for the volumetric efficiency is what? 1 or 100%. Okay, if it's 100%, then the intake fresh charge is exactly the same as the theoretical that the engine can take, but the actual values are lower than 1. Okay? What about the two-stroke? The volumetric efficiency in the four-stroke is the similar to it in two-stroke is called the delivery ratio. Okay? If the engine is naturally aspirated, then the amount that actually enters the engine is by far, or the maximum value of it is the theoretical mass at the reference conditions. Okay? But what if the engine is supercharged or turbocharged? Is the pressure and temperature of the intake air when you use a supercharger, are they lower or similar or higher than the reference conditions? Reference conditions are what? Are the atmospheric pressure and the atmospheric air temperature. When you use a supercharger, are the intake conditions, what are the relations to the reference conditions? They are higher. You have a higher pressure. Okay, so you have a higher mass, so you can charge the engine with higher mass than the theoretical mass. Then at this case, the charging efficiency, will it be a maximum of 1? No, it will be more than 1. Okay, so the charging efficiency and the delivery ratio, they are both, if you are looking at a naturally aspirated engine, they are less than 1. If you are using a supercharged or turbocharged engine, they will be higher than 1. Okay? What are the factors that are affecting the engine charging? The fuel type, fuel to air ratio, mixing temperature, compression ratio, engine speed, intake and exhaust valve designs, valve timing, quasi-static effects, friction effects, ram effects. What are those? Engine charging is, as we mentioned, is removing the exhaust and entering new fresh charge. Okay? If the fuel, it depends on the fuel. Gaseous fuels are easier to mix with air to enter the combustion chamber. Liquid fuels are less in the mixing efficiency with the air. Okay? So the engine charging will be better with gaseous fuels. The fuel to air ratio, it also affects the charging efficiency according to the value of the fuel, the fuel mass inside the engine. The mixing temperature, which is called the heating effect. If the mixing temperature is high, what happens to the charging efficiency? Charging efficiency is mass, the actual mass over the theoretical mass. Theoretical mass at the standard conditions, but the actual mass at the actual conditions. So if the temperature increase, what happens to the mass, to the density? Rho equals P over RT. So if the temperature increases, the density decreases. So the mass decreases. So the charging efficiency decreases as well. Okay? What about the compression ratio? How can it affect the engine charging? If the compression ratio is very high, then the clearance volume will be very low, and you will have longer time to input the intake air, which will improve the charging efficiency. What about the engine speed? As we mentioned, as the speed increases, the available time for the charging decreases. So it will start choking the engine. There will not be enough time for the engine to draw its required amount of air. So as the speed increases, the charging efficiency decreases. Okay? Intake and exhaust valve designs, they affect the charging efficiency. If they are well designed to streamline the intake air and the exit exhaust, the charging efficiency will increase. Okay? Valve timing, okay, which is the backflow effect. We know that the intake and exhaust valves have overlapping times. Okay, so if this overlap is minimized, no flow will go from any valve to the other, and it will increase the engine efficiency. There are also quasi-static effects, which is factors that affect the volumetric efficiency without depending on speed, like vapor pressure. If vapor pressure increased, okay, it will change the the intake air has humidity. Okay, so as the humidity level increase or changes, it affects the combustion and the intake efficiency. The friction effects, of course, if the valves and the air passes through the intake manifold, the valves, and enters the cylinder, and it also passes through the throttle valve. If all these components create friction between its surfaces and the entering air, if this friction is high, it could choke the charging amount of the engine. Okay, ramp effect, which is due to the fast movement of the valves at high speeds, it affects the engine charging. At very high speeds, the valves, you know the valve, how does the valve open and close? The cam pushes down against the spring, and when the cam leaves the valve, the spring pushes it back. Okay? If the engine is running at very high speed, the valves are open and close very fast. Okay? When the valve is pushed back by the spring at very high speed, it disturbs the remaining entering flow of the air. So it reduces the charging efficiency. This curves shows how all these previous factors affect the charging efficiency from the volumetric efficiency from 100% at the top, and as you add one or more efficiency from these types, and some of them depend on the RPM, which is related to the mean piston speed. So as the RPM changes and increases, the volumetric efficiency what? Decreases dramatically. Okay? I want to ask you something. At lower speeds, why is the volumetric efficiency lower? You see that at low speed, what is increasing the volumetric efficiency? The backflow effect. شافتك ولا ايه؟ هي عايزة تمشي أكيد. ماشي. خلاص يعني عند السرعات القليلة احنا قلنا في اوفرلاب ما بين الفالفات. الاوفرلاب ده بيبقى بالكرانك انجلز. لو السرعة قليلة بيبقى الوقت كبير يسمح ان في فلو بالسرعه اللي يدخل من الانتيك ويطلع على مين؟ على الاكزوست. تمام؟ احنا كده ناقصنا قد ايه؟ بصوا عشان يعني انا بس